explain what is scalar curvature, and I'm certainly in a very difficult position because I'm convinced I don't know what it is. Yeah, so I have to explain you what you don't know. On the other hand, I must say that's okay because I think as Pauli was speaking about physics, that the only thing kind of to make progress in physics is just to acquire higher and higher level of non-understanding. And that's just difference between science and kind of common life. And in life you achieve understanding, and in science you're not supposed. If you arrive at understanding, it means something wrong with you. I mean, so you're not supposed to understand. Okay. So we have this concept of scalar curvature. So we first give a wrong definition. It will be wrong, but very kind of elegant. Yeah. And so our objects are Riemannian manifold X, and they have Riemannian metric, must be smooth. And you assign to this Riemannian metric some function which will be scalar curvature on X depending on this metric. So it's a function. So it's assigning function of manifolds which is kind of pleasant. And maybe I have to put it in this order. And the basic property of this is additivity. The scalar curvature of X times Y equals scalar curvature of X plus scalar Y. This unquestionably very nice property. Nobody can argue. Eh? It's a very good property. Another characteristic feature of this, that if you scale the manifold by constant lambda, meaning distances go by lambda, I always forget what it means, lambda squared for G, this implies your scalar curvature goes to 1 over lambda squared. What was before. So when you make manifold larger, curvature scales quadratically exactly as you would expect for a curvature. And also that is okay. And then there is the last condition. And this is kind of where this already kind of okay. Okay, excuse me. It's hot here. I mean, just and the last property is as follows. So if you have two manifolds and you have this condition of the same dimension, if you have this inequality and you take this point X and this point Y, then if you take small balls of the same radius, sufficiently small, then this ball will be smaller than this ball, volume-wise. Okay? So if you have this inequality strict, whenever you make curvature bigger, small ball become volume-wise smaller. And that's almost the end of the story, except you need some normalization. And normalization you have to do is that if you have two-dimensional sphere, the only normalization, S2, then scalar curvature, because of constant. I did another condition which I kind of always had in mind, never said. It's not isometry invariant. It must be invariant under isometry. It's kind of. So simple, you can forget it. So here it must be constant because C is homogeneous, and this scalar curvature of S2 of unit sphere must be 2. It's some reason to say 2 rather than 1. It is, but of course it's kind of convention. And the moment you said it's uniquely defined, for example, and there's this exercise which should be made, that scalar curvature of n-dimensional sphere will be n times n minus 1, which actually kind of some exercise, right? Why it is so? Or if you have hyperbolic space, of dimension n with usual section curvature minus 1, section curvature equal minus 1, then scalar curvature equals minus n minus 1. It's a little kind of elementary computations, but they tell you something, that this definition, which everything was kind of here quite nice and natural, except for this business about balls, yeah. And so there's a tendency to think about scalar curvature in terms of balls and their volumes, but never ever anything came out of it, I must say, yeah? For a variety of reasons. So that's how it is. So what we want to, right, so what we want to understand, yeah. First, we do know that if you don't this interesting phenomena happen only, and this are not only for scalar curvature, but other curvatures, usually with one-sided bound. So the interesting condition in scalar curvature of manifold, say positive or this, or even greater some constant, might be positive or negative, and then something happens. You know, opposite inequalities doesn't seem to be of any relevance. So we concentrate on that. So in a second, I explain why. And so we want to understand what does it mean for a manifold to find a kind of good definition that scalar curvature is positive, for example, or non-negative. So again, I say we have manifold, and we want to have scalar curvature greater than 0, for example. And here is a question. And so what I want to kind of switch my question and to say, yeah, but, and again, I will justify it partly why I make the switch. But what about that? What does it mean to be a manifold? And so manifold must be kind of nice, interesting geometric object incorporating much what we do. And there is traditional concept of Riemannian manifold and whatever. And but I don't think it's adequate for the study of scalar curvature. So I need a really new concept. A new meaning very, very new, very different. It will be some eventually, I'm not going to convince you, but suggest it will be not a space at all, right? It will be something more abstract, kind of vaguely, vaguely. And I give some indication what you may want. But before going into that, let me say bring up some simple examples, which has been already mentioned to some people in the narrow circles. So what we know, what kind of nice object emerge for other kind of curvatures, namely, if we want to understand sectional curvature, say greater or equal than something, some kappa, or for this purpose, or less than or equal than kappa. Right. So how we define that? So again, we start with a model case. When you have a real line, we postulate it has any curvature you want. You can assign it any curvature. It may be either plus or minus infinity, depending on, so anything will be true, right? It's in what I'm going to say next. Secondly, if I take sphere, its curvature +1. And you have a hyperbolic space, its curvature is -1. That's kind of definition. And then you want to give from that and from give kind of natural definition of curvature for all spaces. And then you make the following axiom, if you wish, which in fact is a theorem, axiom, motivated by, on one hand, theorem of Kirsch-Baum, and then a generalization by Schroderick, I think with length, and also somebody else, I guess, saying that. I say slightly uncarefully, yeah, just because, but this will be immaterial. So I have one space, and here is curvature. If this is greater or equal than kappa, and I have space-wise, and here is sectional curvature. Maybe I say it better. Sectional curvature of x greater or equal than kappa. Yeah, if you don't write formulas, there is no point to use the letters. Yeah, letters are just, it's a very stupid thing to use. Yeah, it's laziness, because you're lazy from the point of view of author, so the reader, let the reader suffer. And then actually, when I see paper and then people may not lose, I don't read it. Yeah, I mean, it's their business to make it readable, so you don't have to remember notations. Sectional curvature greater than kappa, and here is for y opposite sectional curvature less or equal than kappa. And so I define this situation. And then the property is, if I have any subset here, x0, and I have any map here, f, such that it is distance decreasing, or Lipschitz constant of f less or equal than 1, so the mean dilation of a map, then it extends to the whole space. Also with the same condition. So extendability is very kind of categorical definition. So if you work at if you think about metric spaces as object of a category where morphisms are distance decreasing maps, this gives you perfect definition, except, of course, for normalization. Otherwise, it would be a little bit vacuous. However, even without normalization, it's pretty neat. So this is a definition. In order to justify it, it must be justified for simplest example. Whatever curvature is, it must be 0 for Euclidean space because scale invariant. Any curvature must scale invariant. So in particular, it implies what I said, that if I have in Euclidean space any subset, and I have a map to another Euclidean space, which is distance decreasing on this subset, then it extends here with the same property. And this is a theorem. And this is non-trivial theorem by Kirschbaum, which kind of motivation of what I said, which says that it is remarkable functorial property in the Euclidean metric, right? So in Euclidean geometry, there are not so many fundamental theorems, and this is a probably number 2 or number 3 kind of basic Euclidean theorem, right? It's not that it's not well known as much as it deserves. Yeah, it's very, very simple, very remarkable, and absolutely non-counterintuitive property. If you hear it for the first time, you suppose you don't believe it. Yeah? If you know a little bit the subject matter. Yeah? Right? If you believe it, it means you never thought about that. So, and the proof is simple, but it's kind of simple. But you have to know that. Yeah? It's not something you can. I'm not going to repeat it. I will certainly make a mistake. Yeah? It's little computation there. Yeah? Pythagorean theorem, of course. Of course, it depends on Pythagorean theorem, like everything. Okay, so that's and something like that we want to have, right? And then there is the developed theory of, so you see, it's just metric space. I don't make any really kind of assumption about the space a priori. You see, with this, it would imply there are J-sec and Taratai, and then you have to prove, say, convex surfaces. For example, convex surfaces have positive curvature, and therefore, if this is convex surface and then it goes to Euclidean space for intrinsic metric, it has this property. It's already a quite profound theorem. You never prove it directly. Yeah? So it is a really very, very, very ingenious theorem of Kirschbaum and its generalization. Yeah? Because you know certainly some definition of curvature, you know, comparison, triangle, whatever, but this is just kind of a kindergarten. Yeah? Everything sits in there. And that's because you see, definition which depends. You see this, like any intelligent definition. Inside there is very non-trivial fact which makes sense of this definition. It's not just something else. So it's a very, very, very remarkable class. And then indeed there is a very developed theory on both positive and negative curvature. And these are spaces, they are metric spaces. And they're quite well understood. Well, not fully, but rather well understood. They're about distances. But now, so what we know about scalar curvature? This is what we know about from other curvature, basic curvature condition. And so nothing was really known, except, of course, on the formal level, it was entering some variational principle, and was the most fundamental was, of course, derivation of Einstein equation by Hilbert, who actually derived before Einstein from variational principle of scalar curvature. So Einstein metric are critical for the scalar curvature, which again is not kind of that simple. Yeah, it's somewhat counter. If you think about nature of variational equations, it's counterintuitive because if you do it uncarefully, you never get this equation. There'll be some cancellation, which happens when it works because you have so it get the same order, all kind of high order term cancel, but it's in the formal level. But on the geometric level, nothing was known unless discovery of Dirac operator, but this, of course, essential part of the discovery was, of course, IHES Singer. So, because I think that the Dirac operator we use in Riemannian geometry were actually discovered by IHES Singer. It wasn't a Dirac wrote some formula of the Euclidean space. There was some matrices, but the form, which is essential, that there is a universal elliptic operator, and of course Dirac was writing it over space-time, which is not elliptic operator anyway. But this was a major discovery of IHES Singer, this Dirac operator. Index theorem is a kind of little thing there compared to the discovery of Dirac operator, which is misunderstood. The existence of index formula is obvious. And there is topological formula, exactly shape of this is just kind of exercise. But it makes sense only because there is remarkable, and there are some other elliptic complexes, of course, but there is universal operator. So there is Dirac operator. And Dirac operator, it was actually known before Archer-Singer, in a elliptic context, back to Schrödinger, there is some formula related Dirac operator to Laplace operator. And then it was discovered by Lichnerovitz, immediately combined with this Archer-Singer theorem. So what is this operator? So the beauty of that, you don't have to know what the operator is. You have to know it exists. Yeah? So you have a manifold X. And then there are some bundles, the kind of spinor bundles. You don't have to know what they are. That's bundle associated with tangent bundle of your manifold. So I build it out to something like tensors. They're spinors. So what are spinors? So again, you can give a definition, which kind of not that difficult, which I actually don't even remember, but you don't understand what they are. You cannot explain. And I was suffering for that for a while, unless I met at some moment Michael Attier, and he said, well, nobody understands what spinor is. You're not supposed to understand it, yeah? You just live with that. It's okay. It's like differential form, you understand. It's just form, volume. You don't understand what spinors are. But okay, you don't understand it. But you know they're there, right? So, so there are spinor bundles, and there are sections over your manifold, and there is differential operator. Yeah, call it Dirac plus, because there is also operator going in that direction. Dirac minus, all together they make the whole spin to the spin, but it's material. And so this is elliptic differential operator of the third order. And there is one little catch to this, and of course physicists could have known that implicitly, but they never worked on manifold, I believe, because it's appeared on the Euclidean space, and both, I think, both Schrödinger and, no, but probably Schrödinger was considering over Riemannian manifold already, but it was something contractible. You need manifold to be spin. Now, what does it mean manifold to be spin first? Yeah? What is spin manifold? So a manifold is spin. If it means certain bundle, stands in bundle is spin. So what does it mean bundle being spin? And then you look at surfaces, orientable or not, and say that a bundle, high dimensional bundle of this surface is spin if it is trivial, and it is non-spin if non-trivial. Because stably there are only two kinds of bundles of a surface, right? Trivial, non-trivial, spin, non-spin. That's it. Yeah? And if you have high dimensional manifold, you take surfaces inside, restrict tangent bundle to the surface, and ask whether it's spin or non-spin. So if it's spin for all surfaces, manifold spin. If not, it's non-spin. And of course, the key example of a spin, non-spin bundle is of a sphere. Of a sphere, the Hopf bundle is non-spin, but tangent bundle is spin. Twice of this bundle, right? And that's a basic example: spin, non-spin. So for many purposes, you only don't have to look any surface, just only for spheres. Well, some application is sufficient to have those spheres. To have a restriction of a tangent bundle to all spheres to be spin, to be not like Hopf bundle. So manifold is spin. If restriction to any surface, it's not like Hopf bundle. Is slightly more simple than that. So that's conceptual spin. Because otherwise, when you define Dirac operator locally, you write some formulas, but when you start merging them together, if you go around surface, which is on spin, some sign is not defined. Operator defined only up to a sign. This looks little nuisance, but it's really fundamental, right? For some reason, it's spin fundamental in physics, and it's fundamental in this kind of story, and of course, why physics abides this logic, or mathematics follows physics, we don't understand. And it's kind of one of the miracles of the world, yeah. Have to be accepted, like, without understanding. And then, so there is this operator. And then there is a theorem, computational formula of Archer-Singer saying that this operator sometimes has non-zero index. So it means that there are non-trivial solutions to this equation. Because there is non-zero index, a positive index, which means there is implying. So, for example, we can reverse the sign if you go this direction. But so if index non-zero, then either in this or in this direction there are non-trivial spinors. So in any case, this operator will have kernel, which is call it just d, and then d squared also will have a kernel. And it's again little computation because operator is elliptic, or if you need something else, kernel here or kernel here is the same. D being having so harmonic spinors, it's the same to say d of them equals 0 to d squared equal to 0. Right? It's little kind of integration by parts involved. It's not algebra. At this moment, by the way, I use a little bit piece of analysis here. Much of that is, of course, algebra. Definition of Dirac is very much an algebra. So, and the same year, I think, when more or less when this was done by IHES, the appears paper by Khnerovis, he reproduced again this formula of Schrödinger, say that d squared equal to properly understood Laplace operator plus 1/4 of the scalar curvature. So, and that is kind of where scalar curvature enters. And so what's remarkable here, that this operator, the d may have non-trivial index. It's really linked to topology. And the index of operator expressed in topological invariance of manifolds. Now, first, what this identity means. Yeah, you have to understand what the d squared. So it's we have manifold, and we have some vector bundle, as it's associated with the tangent bundle, but just some vector bundle. All you have to know. And this connection coming from Levitsky connection, and out of this you define this operator. Now, this some operator. About this operator, we don't know how it's defined. Right? We're not supposed to say. It's just operator with this property. It may have, for topological reason, may have non-zero index, meaning whatever metric you take on manifold, whatever you do, because pure topological, always there must be harmonic spinors. Harmonic meaning satisfying equation d squared of the function 0. All you have to know. Which is satisfying. You don't have to know much here at this point. And what this operator, much easier to describe, this operator. This is scalar multiplication. I'm sorry, 1/4. I'm sorry. With our normalization of scalar curvature, for some reason, this kind of it's 1/4. And this is essentially Laplace operator, but you have to you say what kind of Laplace operator is this. And so what we have a Riemannian manifold, we have vector bundle, and we have connection in this bundle. The moment we have connection, we can say what is horizontal section and how much it deviates from horizontal. And therefore, there is concepts of gradient or norm of the gradient. In particular, for any function, you can say to take the gradient. So how much, what is the derivative? Take it squared and integrate over domains here. So you have this Hilbert norm. Yeah. So I have this quadratic form. And then you can write any quadratic form can be written as some operator. And this is my delta squared, f times f. So if you take, say, function with compact support, you always, any quadratic form, differential quadratic form, can be written this way. And this is now linear operator. And Laplace operator appears, of course, in this shape. So it's like usual Laplace operator. So again, you don't quite understand what kind of harmonic sections are, but you know what is a quadratic form. It's just like that, on one hand. And so, and this operator by nature is, of course, positive. You see, this positive expression. It defines positive. Therefore, it follows that if this term is positive, this is kind of, to be precisely, non-negative, yeah? But this is strictly positive, so this will be positive, no zeros, right? So we have conflict with IHES theorem. If IHES theorem predicts there must be sections, harmonic sections, this category there is no harmonic sections. So in this way, you find an example of manifolds which do not admit compact manifold of metric and positive scalar curvature. And the first example was a K3 surface. So if I'm not mistaken, yeah, in the complex surface given by equation z1 to the 4 plus z2 to the 4 plus z3 to the 4, right? It's surface, so it might be. We have to add another term. I always forget. Yeah, it's 3 or 4. So it's in projective 3 space surface. So plus z4 to the 4. Yeah. This is in homogeneous coordinates. So it's a surface of degree 4 in the complex C3 space. So in CP3, yeah, it have this, it's Kummer surface sitting there. And this is an example, because the simplest example. It is a spin manifold, so it must be spin, and for this to make sense. Interesting enough, all formulas kind of okay, but this, in fact, they don't make sense, right? And this and the next example was when the Archie and Singer they proven more general theorem, the index theorem extended to something else, in particular, they've proven that if you have an exotic sphere, and simultaneously exotic sphere were discovered, I forgot what dimensions, say 8, whichever, which are not boundaries of spin manifolds, right? They also, the Dirac operator there has non-trivial harmonic spins. So these invariant are such to exotic spheres, or to spheres, homotopy spheres, whether they admit or don't admit spin filling. And if this invariant non-zero, meaning they don't admit such thing, then there are harmonic spins. And then immediately Hitchin was kind of observing there are exotic spheres which have no scalar curvature, metric with positive scalar curvature. And we don't know for others, right? And typically we don't know which of them have and which of them don't have. Some of them apparently have such metric, some not, and it's very unclear. It's a very, very subtle invariant, mod 2 invariant, yeah, actually. Yes or no, mod 2 invariant. They connect the sum of the two, it disappears. And this, on the other hand, very robust. This is quite a robust invariant. Because this is some heap abstraction, some Pantagin number. So if there is a, in dimension 4, actually it says if you have a 4-dimensional manifold spin and with non-zero Pantagin number, first Pantagin number, then it has no metric of positive scalar curvature. And Hitch invariant more subtle. And so it looks very kind of strange and very exotic and very kind of mysterious, and it was very perplexing because you cannot prove much stronger conjecture that say question if you have exotic spheres with positive sectional curvature. And there's nothing you can say about that. There is no abstraction whatsoever, the only abstraction. And scalar curvature is infinitely weaker than that because, and this at this point it was worthwhile mentioning, that you have abundance of manifold of positive scalar curvature because if you take sphere S2 and multiply it by anything because it's additive, and this sphere is small enough, when you multiply it, scalar curvature becomes positive. So it can have any elaborate shape, and this is kind of a model example. But still, there are some limits to that. Yeah. Unlike sectional curvature, which of course, if there is a bad piece here forever, you cannot eliminate this by multiplying or whatever. So it's very average kind of invariant. It says something on the average, nothing individually. However, and this was kind of very much kind of perplexing phenomenon for quite a while. But then came kind of a new wave, and I think this conjecture, Rick, you correct, was by Torpe, who made this conjecture about the torus. Who conjectured that torus, 3 torus has no metric or positive scalar curvature. Or he conjectured for Euclidean space, there is no compact perturbation.
I think it's Garrosh.
Huh?
Robert Garrosh.
How pronounce it?
Garrosh.
Garrosh. I'm sorry, Garrosh. Yeah, it was Garrosh. Yeah, indeed. Yeah. I don't know when I saw in some of his article when he was saying something a little bit motivated by physics, and exactly in dimension 3. He suggests the thing that 3-dimensional space admits non-trivial deformations with such that metric and this bubble become non-negative. So the conjecture was, I guess, that any such perturbation if flats at infinity and standard and here non-negative scalar curvature, then it is flat. So it's just the same, it just don't exist in proper sense, except for change of coordinates. And that was proven with Yao, and then it's become in a very geometric way, in a very transparent and geometric way, into what was kind of a point. And the point was not algebra of that. It was similar to this formula for Dirac operator. So Dirac squared equal this squared plus 1/4 of scalar curvature. And the formula which is involved here is roughly like that. So I formulated in a vague term because I said precisely I make a mistake. So you think how volume of manifold changes when you move manifolds in the normal direction. And so what one knows that this is well controlled by so-called Ricci curvature. And so this may be actually a definition of Ricci curvature, saying that if I have a hypersurface in a smooth manifold which is convex, and I start moving it normally with unit speed, then its volume necessarily decreases. Right? So if you have strictly negative Ricci curvature, this is true, and if and only if, yeah, by the way. Now, if you look at scalar curvature, it's much weaker invariant. Of course, it is not true. However, it compensated by scalar curvature inside of what happens inside. So So to speak, I'm just cheating. If in the course of this deformation, this scalar curvature was, I'm saying something wrong, maybe I will correct it maybe later on. Say if it happened to be negative, the same is true. That either volume goes down or this curvature here in a way positive. Yeah, it's not true exactly being positive, but kind of in a way tend to be positive, close to be positive. So it is something not about space of curve or distances, but just in the space of hypersurfaces, there are variations in just interacting exterior and interior intrinsic curvature. And when it was kind of going through kind of the rigorous statement, this is kind of very simple, beautiful lemma, is saying that in dimension 3, and first one may observe that this thing about non-compact manifold, but it can be reformulated in terms of compact manifold, saying if we have a torus, say in dimension 3, it cannot have metric of positive scalar curvature, because if you have such a bubble, you can make the bubble periodic everywhere, divide by gamma, and have the bubble on the torus. And this is so for the torus is more transparent, compact, easier to handle. So imagine you have positive scalar curvature, and then this argument shown you originally used some different, I think, variational principle. You know by geometric measure theory that any homology class can be realized by minimal surface. Right? And then because minimal surface is absolutely minimizing this surface. So if you move it in this normal direction, its volume must go up. And then you just compute, so what is this variation? And the formula being involving the scalar curvature of the same nature computation which involves the Dirac operator. So there is remarkable formula, Gauss formula related there, saying that if you integrate this variation of the volume, what you actually get, integral of the intrinsic curvature of the minus scalar curvature ambient space with some coefficient. It will be 1/2 rather than 1/4, I guess. Yeah. Therefore, if you have such a thing, and you know it's absolutely really minimizing, and you push it, then the integral of the curvature of that must be positive, which implies that this manifold must be sphere. But no homology class can be realized by a sphere in the torus, because our torus is just the universal covering contractible, all spherical classes are contractible. And that's kind of a logic of that. And this is a kind of really very geometric and very transparent. And so it was pushed by Shantiao by now to all dimensions and by induction. So which is not exactly how it works now, but in spirit it still works this way. That if you have high dimensional manifold of positive scalar curvature, you take minimizing hypersurface. Then if it's non-singular, you know with some induced metric can be modified to have positive scalar curvature. If high dimension is still unknown, yeah, but it's almost true. Right? It's proven equivalent to that, which is sufficient for applications. And then you know manifold like n-dimensional tori don't have metric of positive scalar curvature. And this has nothing to do not only with technically, but with conclusion of that. You see, this is a statement would apply to any manifold homotopy equivalent of the torus. Or, moreover, to any manifold which admits a map of degree 1 to the torus. It says such manifold have no metric of positive scalar curvature. And here it's very kind of subtle, smooth theorem. On the other hand, it's not stable on the map of positive degree. If you map, because you take usual sphere, and usual sphere has metric of positive scalar curvature, homotopy equivalent. So this is not homotopy invariant. Even this one in dimension 4, first Pentragian number, is a homotopy invariant. If you go already to dimension 8, corresponding this similar abstraction, it's some combination of another Pentragian number, which is not homotopy invariant anymore, at least for simply connect manifold. So it is very, very different kind of theorems. And they give you kind of very, very different flavors. So how much time I have? Let me see. Where I am. So I have 25 minutes here. Okay. So that's how it is. And then, so what we can, next, how coming back to the Dirac operator. So that's a kind of actually in the form they suggested, none of them tells you much about geometry of the manifold. This, however, if you look closer, tells you quite a bit about geometry. But this Dirac operator approach tells you nothing about geometry of the manifold. You just go immediately to topology via index theorem. It's very hard to extract any geometric information about this manifold. But then, so what comes next? And then there is a kind of quite interesting parallel with the phenomenon first observed by Lustig a long time ago, responding to that question by Novikov about the so-called Novikov conjecture. So, as I said before, this invariance produced abstractions abused by index theory. They all, even forgetting about the very subtle thing about Hitchin, in a manifold dimension 4K, when there is usual index theorem, they say that if certain Pantagin number of manifold called a root genus, whatever, some particular combination, which has meaning of which I never could understand, which is not so obvious, it's not supposed to be easily understood, being non-zero, and manifold the spin, then there is no scalar curvature greater than 0, and if it is flat, then you know more or less what it is. But starting if manifold is simply connected and dimension is bigger than this more than 1 from 8 on, it is not homotopy invariant. You always can change your differentiable structure and make invariant whatever you want. And this was known for quite a while. And by work by Browder, by the way, and I think already follows from Browder and Novikov for surgery, that simply connected manifold, there is no constraint on their Pantagin classes or Russian Pantagin classes except for the signature theorem. So the signature of a manifold is a signature on dimension 4K of the quadratic form, intersection form, how many plus and minuses, which is by Tom Hirzebruch theorem, is again some Pantagin number, combination of Pantagin numbers, and that's the only invariant. And everything else is flexible. Right? So the simply connected topology tells you that there is nothing non-trivial in being smooth manifold in high dimensions. By the way, of course, we know it's very different dimension 4. It's a whole world of that. But this theorem actually says simply connected manifold in high dimension trivial. It is not all invariants are pure algebraic topology. You take homotopy type, you take any bundle you want with one constraint, you always can make manifold or unmake it. So it's very flexible kind of stuff. And so for that reason, this subject died off, because it's finished. That's it. Very simple. However, and this was conjecture by Novikov, that it is not true for non-simply connected manifold. And in particular, one of what he's proven, which I don't think was kind of clear a priori, if you take n-dimensional torus and take, he proved something more powerful, but if you take any manifold homotopy equivalent to this, it also will have trivial Pantagin classes, rational Pantagin classes. You cannot create non-trivial Pantagin class on the torus. For non-simply connected, for simply connected, you can do it. Yeah, if you replace it, the torus by product of spheres, then easily you can produce new differentiable structure. You have any Pantagin class you want, except for signature, which remains 0. But for torus, you cannot do that. And his conjecture is, again, his conjecture is slightly stronger than that, but in particular, he suggests that this must be true for all the spherical manifold. So you have a manifold X such that universal covering is contractible. And then the conjecture is that its Pantagin classes are homotopy invariant, rational Pantagin classes. You cannot change them. They are defined uniquely by the fundamental group. So the fundamental group alone knows what are Pantagin classes, right? And Lustig proved in one particular case, and so by now we know the discussion very parallel what happens with Scalar Curvature, and uses index theorem, but kind of perpendicular direction to one which is used in the argument by Lichnerovich. So Lichnerovich relies on this part. So index theorem, let me remind the shape of the index theorem, which applies. So one remarkable thing of index theorem, when you have Dirac operator or any other differential operator or manifold, defined over some bundle, over X. And you have another, say, complex or real vector bundle here. Then you always can take tensor product of this operator with this bundle. So which will act, in the case of the Dirac operator, from spin bundle tensor product with L. So I can think you can see the spinors with value in this bundle, right? And so this is canonical operation. And then there is an index. And then this index become, in fact, not a number, right, but a functor. You assign a number to each L. So it becomes what people say element of K homology of the manifold. So a dual to vector bundles, right? So to which vector bundle assign a number, and it's kind of functorial, additive, multiplicative, etc. And so it's a really element of K homology of the manifold. And then there is even a better kind of next level of that, right? So in this case, the formula is the following. When you twist it, the index of the operator involve this A roof of manifold, something depending on the tangent bundle, some characteristic number here, plus Chern character of L. And this is a very kind of simple thing. Yeah, it depends only on the bundle, doesn't depend on the manifold. And it's very simple natural invariant. It's additive for adding bundle, multiplicative for multiplication bundle, tensor product. It's uniquely defined by normalization. Very natural thing, yeah, right? And so this is the formula. So there are very different terms. And this easy kind of part in the proof, it's easy to prove that index behave with respect to Chern. And hard part is here, and which involves smooth invariant. This doesn't involve smooth invariant. Much coarser theory, which needed to study that. And it's originally how it was done by Herzebruch when he proved Riemann-Roch theorem. He was first proving, like in classical Riemann-Roch, what happens when you deform your bundle, deform your kind of domain, so you're twisted by some bundle, and then you need some normalization case to get this formula, and then he was using the Tom Herzebruch-Kaborim theory. So there are two different kind of this index theorem is highly non-homogeneous. There are two terms of very different nature and give you very different information, right? And then there is even next step to that, which also was in the work with IHES Singer, when you have instead of one operator, you have family of manifolds with bundles and with operators. So you have family of manifolds and bundle moves. You change the bundle, and then you consider in each of them, you consider your index. Index you think about now not a number, but you have kernel and co-kernel. And take the formal difference between them. So the formal difference of two bundles over the base. However, they may change their dimension, but that's kind of immaterial here. You can compensate for that. So you really have vector bundle, a virtual vector bundle of the base. And so index now takes value in K theory of this base. And then there was a next step, and when this was algebra of functions, because you can express K theory of a space in terms of K theory of the ring of functions. And now it's an aha. Now we can take any sister algebra, which is non-commutative algebra formula like that, and still there is index theory. And then maybe, don't know well, I wouldn't talk about that. Yeah. But then there is very big extension. But this particular instance give you something, tell you something about, it was applied to Lustig to torus, and he kind of could recapture theorem of Novikov, because you can, so the torus itself, from point of view of index theorem, is completely kind of empty, because there is no harmonic spinors here. The harmonic spin is constant, because it's parallelizable manifold, flat parallelizable. So spin is the same as harmonic function. There is no non-constant harmonic function on the torus, 0. So it doesn't seem you can index tells anything to you. However, there is a family of vector bundles here, line vector bundles, hitting here, where theta is parameter in the dual torus. I don't know how to call the dual torus. So they correspond the complex flat bundles, so the circle bundles, and the circle bundles corresponds to homomorphism of the fundamental group of the torus to the circle. Yeah? This is the dual torus. And so you can, right? So what is the angle? This angle corresponds to this homomorphism. I keep forgetting that. So this is a continuous family, and so you have now this torus cross torus, so to speak. Yeah, this is dual torus over this dual torus, And over each point you have this our torus, but our torus carries now this line bundle, which is flat bundle, right? So this monodromy around the torus tell how it turns this circle. And for this family, index is non-zero. For this family, index is non-zero. So it means now that over torus have a family of flat vector bundles, and some of them must have this harmonic section, and this would be true for any metric in the torus. No matter which metric on the torus you take, there is some flat vector bundle, circular bundle, where there will be harmonic spinors. But then you apply the Mikhail formula. Now this bundle is the same. Locally, it's the same as no bundle at all. It's flat bundle. So locally, Dirac operator is the same. So it's usual Dirac operator. You apply this formula, and you see that torus contains the metric of positive scalar curvature. And here it must be understood. See, it's also torus, or anything which goes to the torus with positive degree. It's very kind of general, the same as this case, with distinction. If you, for torus, it's the same, but if you map other manifold, it must be spin. Okay? Yes, everything looks okay, because at some moment to make sense of what you say, it must be spin. It's extremely annoying, because we believe it shouldn't be spin. Because if it comes to a Lichnerovich theorem, the spin condition is crucial. The part which involves this a roof part of the index formula, spin is crucial. Here, for all we know, it's irrelevant. And now we can eliminate it by using minimal surfaces. You know it's irrelevant. Sometimes we don't know. So what is kind of you see here that in both cases, if you look at this kind of closer, so what's very annoying in both cases? Here it's annoying because we come to this minimal surface and we don't know what happens outside of the manifold. We just know by this minimization process, there's no idea what happens inside. Manifold is a horrible mess, and we forget about all manifold, only concentrate on this minimal surface. In that argue to what happens. And here you have the spin, and you have a Dirac operator which knows nothing about manifold. So in both cases, we don't know much about that doesn't tell you much about manifold. Here it tells you slightly more, as we shall see later. So, so what now we want to do with this? The remaining 5 minutes, I want to say what kind of spaces you want to eventually have, and then there is a chance they're related. So one thing I want to say that there is the following, and this is actually the thing, the story is more involved. I didn't tell you the whole story and the results, but no means included in that. And it is there is much more to the story, and this only maybe half of the story. And it's or beginning of the half, I would say. It's not half what I told you, the beginning of the directions, but there are other directions at all. And so from what we already see, there is this kind of picture. Here is everything related to a roof. The index theorem to a roof. Here is coming minimal surfaces approach. And here is what corresponding to the Chern of the twisted bundle for this operator, twisted bundle. And this may be tricky. It may be not really a number, not a Chern class, but some element of some K theory or whatever. But it depends on the twisting with somebody, not with the smooth structure. So here smooth structure is not involved. We cannot avoid using it, which is even conjecturally it's unclear how to say it without smooth structure. However, we know it doesn't enter in the answer. Right? Here, in the minimal surface case, in principle, you can formulate it for manifold for objects which are not smooth. Right? We don't know how to prove this, but this, in principle, the logic of the proof does not insist that the object must be smooth, must be singular spaces. And here singularities appear. And so what is kind of one way you can imagine so what might happening. There may be other actually bifurcations. Yeah, in the theory there are further kind of bifurcation about which I don't say them. It's like different branches. You know, this motivate, of course, you know, what is the tree of life, how it looks like. Right? It's like tree of life, you know, just a little relaxing, because recently I was much learning biology, yeah? So, what are three major branches of life, you know? What they are? They. Bacteria, archaea, and here is prokaryotes, or eukaryotes, I'm sorry. That's including ourselves. Now, what happens here? Then there are these branches. These are amoebas, etc. Then there is branch trees. multicellular. These plants. Then goes mushrooms, etc. Yeah, and then there are animals. And somewhere here there are kind of primates in ourselves. Yeah, it's a tiny, 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 negligible, invisible thing. Yeah, and the here is huge numbers. This bacteria, much bigger. Yeah, are here smaller. Yeah, but this certainly dominant. Yeah, and of course, over all of this in the world of viruses. Yeah, this is kind of dominant. Yeah, the most life, quasi-life, is in viruses in the world. Yeah, and then there are bacteria, and then it's kind of like, so that's, and this is not exactly so far, not so developed. Yeah, this is so behind it. Okay, so what maybe dreamed of? Yeah, what I'm saying now, what you want to have. In the case of, so there are two methods, so minimal surfaces and Dirac operator. In self-dimension 4, when there is Cyber-Witten equation, which I don't know much, so I cannot say much. So for minimal surfaces, so the point is you want to understand, and this is kind of now well kind of much analyzed in the recent paper by Shu and Yao. You have the following coverage: you have flags of manifold, manifold, submanifold, and submanifold, and how they move in the space and each move within each other. And so there is, so you take these objects, flags, manifold, submanifold, 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 ends somewhere, and where it ends is not quite clear. And this move in the manifold, and they move within each of them. And you want to know how their volumes or weighted volume behave. And this is your object. So you have to imagine such an object. You have this very formal operation. There is no metric, no anything. But there are these moving creatures and how they interact among themselves. And I know how to formulate that. And they never come to curves. They live in the basic, of course, say in dimension 3, maybe just space of surfaces inside of 3 manifolds. But you forget about 3 manifolds. You only want to know how the space works and how it's organized. And it's in keeping track of scalar curvature, how it changes, how volume changes, and simultaneously how scalar curvature in this submanifold changes. Right? So this you're imagining mathematical objects involved. They are not manifold. They are not spaces. They will be just functors from combinatorics or whatever of this somewhere else, say in numbers. I don't know what it is. Yeah. But it will be not really, it's not spatial objects. Yeah. They very, very formally want to analyze it. If you do this correctly, maybe you can recover all the theory, and it will be kind of much more general and powerful than we know it today. And there are reasonable indication, especially in the recent work by Shen Yao, who proved some fundamental technical results, regularity for that, which are not final, but certainly go quite far. It's one direction. And this for minimal surface. Now, what about Dirac? And here you have to try to understand in simple terms what Dirac is and what are Clifford algebras. And you know it depends on the parallel transport. And then you just say just 2 words what we may do. So here there are 2 points one has to keep in mind. And one of that, which it is a Kaas-Feynman formula. I don't know which Kaas is written, Kaas-Feynman formula for this operator which I was writing there. You remember the Laplace operator in the vector bundle. So you have a manifold, you have a vector bundle, and you want to understand this Laplace operator in the bundle in terms of the background Laplace operator. And instead of understanding this Laplace operator, you understand corresponding heat kernel. So you know if you start with a piece of heat, how it distributes here, knowing how it is being distributed downstairs. And the answer is quite beautiful. So what you do, you can see the random path here with respect to the Wiener measure, and then kind of nice theorem. You can make parallel transport over this path, and this will be your heat kernel upstairs. And then, of course, you take, so I take the average over the path. So in order to know what heat, you have to know what is a kind of random propagation of that, and this is just covering by parallel transport over that. And this is a kind of basic formula in mathematics. Again, is not known to all physicists and not to all mathematicians. Yeah. It is a really kind of basic formula, right? I mean, in this kind of mathematics, and very, very powerful and very informative. And then another concept which is I just learned at some point from Kontsevich, is how we can describe Riemannian manifold in a kind of, is motivated by a quantum field theory, by collapsing kind of from going from complex to real, from final integral to Wiener integral. So this Wiener measure, which is of course not, was known about 50 years prior to Wiener, of course, and how we can generalize it. And you can do the following. You can consider arbitrary graph with lengths attached to this, and consider the space of maps of this graph to Riemannian manifold. And this space has natural measure on it, which is correspond to Wiener measure. And for example, it's already not quite trivial. Look at the paths. So you consider all paths which come here. And this conditioning at this point is trivial. So in probability theory, we cannot condition the point. But this space is much more regular. So a measure is well defined. And there are these measures. And if you take kind of subgraph, this natural map from one to another, I'm slightly cheating, so I'll say measure preserving. Might be careful in what sense. Therefore, a Riemannian manifold defines the functor from the category of graph to the category of measure spaces. And you say it's correctly. The way I said it, functor, you can say very easy. In fact, if you write explicitly, it will be 20 or 30 different formulas for green function for Riemannian manifolds. So it's what functorial means lots and lots and lots of identities condensed in this concept. This very kind of efficient way to say it, right? But you say it better, and not that I know how to say it better, but you should say it better. And then you say, now you want to do the same with Dirac operator. That's about Laplace operator. And when I want to say to the Dirac operator, what else here? You have parallel transport in definition of this in Dirac operator. You cannot see it like that. Yeah? And then what I do, I consider my graphs together with flat vector bundles over them, which correspond to my tangent bundle. And flat because all bundles with connection of a one-dimensional thing are flat, and they're defined by monodromy, so they correspond just to a representation of fundamental group. So I have this graph, free group, and I have representation of the group in the orthogonal group. And then accordingly, I consider only those map which agrees with this. So when I lift it, you have this parallel transport. But still, there are those measures. And now, in these terms, I can, in principle, define Dirac operator. Because Dirac operator depends on parallel transport, and you go kind of around kind of tiny little cube, and how go around this little cube, exactly Clifford algebra tells you which kind of path you take and what term you have there. And then you can say, now I don't have my smooth manifold. It may be not much smoothness there, but I have this kind of, again, function from the category graph somewhere, and hopefully smooth structure will disappear. Will be only Clifford algebra or some formalism of this will remain, and we can reconstruct these results without ever mentioning smooth structure and lying manifold. Because there are lots of indications from another perspective, especially from minimal surface theory, that many singular spaces should be considered as spaces with positive scalar curvature. The same as is true for usual sectional curvature. But he is much more relaxed. So I have hugely complicated singularity. So complicated we cannot describe it in the usual language. They're too complicated. But they will come themselves if you properly relax the theory and they come here. And that's what you want to do, to create new concept of a manifold adapted to these two approaches. However, there is no guarantee they would converge. They do interact because when we have a hypersurfaces and we have graphs, they intersect over points. And so there is coupling. And this coupling may give some relationship between them, but it's unclear if it will be perfect. It may be not faithful pairing, but that's the last we want to make. So that's enough.